Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Sambit Roychowdhury with us today. Hey, Sambit.
Hello. Thank you very much. And thank you for having me. It's a great pleasure to be here.
Thank you for being willing to talk about your very lovely article, which we'll get to here in a minute. Sambit, where are you located at these days?
Right now, I'm in Munich.
Munich. Okay. Very cool. Yeah.
So, yeah, please.
I think before that you were in Australia or something?
Yeah, so I am a research scientist for this survey called DINGO, which is Australian Escape Pathfinder survey. I did part of my work and spent part of my position into the International Centre for Radio Astronomy Research in Perth, Australia. And I'm going to complete and finish the rest of my position from here in Munich, from Ludwig Maximilian University.
Very cool. Very cool. So Germany, is spring in the air yet in Germany? Are the trees?
Very much, very much. I'm looking out through the window and the first buds, the first leaves are coming out.
Very good. So I'm in Phoenix and it is March 30th, 2022 as we do this. And spring is definitely in the air here in Phoenix as well. In fact, I have some grapevines off my wall. I grow grapes. And so they're all getting their little buds out and starting to do their thing. So in a few months, I'll have some grapes to share. So very good. Sambit, what do you like to do for research?
So my work, I am trained in radio astronomy. So an observational radio astronomer, specifically looking at the hydrogen 21 centimeter emission line.
Okay.
So I basically, throughout my research career, one of the main focus has been to relate the gas as traced by at H1 21 centimeter line, the atomic gas, to star formation. So yeah, so I've taken various alleyways on that path. And
cool, very cool. And that is going to bring us to this very lovely APJ article. Open access, people, you can go ahead and get it. The variation of the gas content of galaxy groups and pairs compared to isolated galaxies. And Sambit, take us away.
Thanks, Frank. As you can see, this article was, the number of the authors there are from my institute in Australia, who are also working either directly related or on the part of the larger group who work for this DINGO survey, which I'll come to. And also various co-authors spread all around the globe. The thing we have tried to do with this paper is try to take a slightly different approach to a very old problem in terms of how do we try to understand galaxy formation and evolution. So there has been a long-standing idea of, I won't necessarily focus on the abstract. Hopefully the thing will come out as I tell about it. It's basically we measure gas fraction in a certain way and try to relate it to star formation. So one of the main things that people have understood from a long time is that the environment that galaxies reside in quite possibly have an impact on how they evolve. So it starts with the famous things like morphology density relation, or that in dense environments you have higher fraction of so-called evolved galaxies, elliptical galaxies in some sense, because they've used up the gas, or that there are not as many star-forming spirals in denser environments as, say, in the field, things like this. So these came from optical studies, and we have some ideas about what might cause it. There are a plethora of possible scenarios. Many of them have been actually seen in action, which can basically deprive the galaxies of gas in these kind of dense environments. Terms which keep coming and going in various conferences: galaxy harassment, triangulation, interactions, etc., etc. So there are various ways gas can be kind of cut off. The supply of gas can be cut off from galaxies, or literally gas can be dragged off the galaxies.
Right.
So in the same time that we see this, the people have been noticing that, for example, yeah, if you can go down a little bit, that there are issues with the time scales of the processes. That most of the these kind of processes happen relatively quickly, other than things that happen in a means these kind of very fast processes that happen in the dense environments.
Yeah.
But that doesn't seem to be tie up with when these galaxies seem to have been quenched compared to how long they are in this group environment or cluster environment. More importantly, of course, since the gas is affected, there have been studies of the gas, particularly the atomic hydrogen, which is the basic fuel for star formation.
Okay.
There are models for going from directly from atomic hydrogen to stars, but generally it's well understood, at least in the present epoch or in the recent epochs, they probably go through the intermediate step of molecular hydrogen. So atomic hydrogen converts to molecular hydrogen, which converts to stars. But still, atomic hydrogen is the base fuel. You need it to finally make the stars. So so people have looked at atomic hydrogen in groups and clusters and have seen clear differences, whether in the mass function or in the even in the morphologies, and looking at how the means it's almost seeing the processes in action, like ram pressure stripping is acting on a galaxy or things like that. So the gas has been affected. Now, but still, it's not very clear that, again, what this does, whether it means removes very outlying extra gas in the longer disk, and that gas would have anyway taken quite a long time to get involved in the star formation. Like much of my earlier work was done on this H1 dominated regime, either in dwarf galaxies or in spiral galaxies in the outskirts, very outskirts of spirals, where the atomic hydrogen basically dominates. And for example, there is a clear relation, the so-called Kennicutt-Schmidt relation. It is possibly driven by things like feedback and stuff which set up the physics of those regions, but the time scale is about a 10 gigayear time scale in the sense of how the depletion time, that is called that, how quickly will the gas that is there will be used up given the time, given the speed, the star formation rate at which it's being used up. So it's so this thing, whether it's this gas that was not really participating in star formation anywhere now has been removed, and whether it really has any effect on the overall star formation in the galaxy or secular quiescent processes are at play. So these are big questions that are being trying to be answered by many very interesting works all over the world. And so we try to take a complementary approach.
Okay.
And this comes from the fact that I've started to work with this new survey, and this is a kind of first generation of very interesting surveys that will come up with the square kilometer array and its precursors. So it's thank you for scrolling down. So I'm just jumping a little ahead. It's called the Dingo survey, which is in the next page, I think.
There we go.
Yeah. So it's deep investigation of neutral gas origin. So what will happen is, because neutral gas, even though it's so omnipresent, the 21 centimeter line through which its emission is traced is a very forbidden transition. It's very faint.
Okay.
So in emission, galaxies have been studied to any detail only in the relatively nearby universe, say z equal to 0.1. There have been quite a few studies which have pushed to larger samples to z equal to 0.2.
Okay.
But individual single detections, the furthest away is around 0.4.
Okay.
0.37 actually with the Chile survey. There have been detections through stacking. You take a large number of galaxies in an area and stack. But these kind of studies generally have looked at relatively limited portions of the sky. We are also going to use stacking, but the things like Dingo, which is being done on the Australian SK Pathfinder, the specialty of that is that you're looking at a large area of the sky in one go. So this is a very nice survey instrument.
Yeah.
So the survey has already started. We're well into the pilot stage, and we are going to go very deep and pick up this 21 centimeter emission from, and at least through stacking, if not directly through detections, we'll go very deep up to a Z of around 0.5. So we're really pushing it now. SK will help us push it even further. So this now we're about to reach a stage where we can do these studies of gas and stars in the same statistical manner that was done with these large stellar surveys, etc., SDSS, all those kind of surveys.
Nice.
So this was the motivation. So we are trying to look what, and given my background of gas and star formation, we said, how can we compare gas and star formation? Dingo has just started at that point when this paper came out. So we already had a very good archival survey, which has been the workhorse for H1 astronomers for a long time. Unfortunately, the telescope that made that survey doesn't exist anymore.
Oh, no.
That is the Arecibo dish.
Oh, sure. Yeah. Okay.
But it gave us the alpha survey. If you could please scroll back to the previous page there, where I, in page 2, in the data section, I have just quickly described the alpha survey.
Oh, there we go. Yeah, and
so the idea was that the complementary approach we decided to take was, since we have to we're still not there to do it on individual galaxies, and we are probably looking at, we want to compare what is the difference in gas content and star formation in isolated environments and dense environments. Let's look at overall things. Like, instead of looking at galaxies in groups themselves, look at the total gas content of a group, total gas star formation in a group, and compare it with what is happening in an isolated galaxy outside, say. Okay. Now, of course, you cannot deal with totals because the scales are very different. A group might have multiple galaxies, so that it will have much higher total stellar mass, much higher total stellar star formation, etc. So we move from this total to an average quantity, which will be described later also. So you basically take the averages of gas content, each one content. I'm sorry that I'm mentioning gas, because gas has, as I briefly mentioned, multiple phases. Molecular gas is more directly connected to star formation, but when in this work, I am exclusively talking about atomic hydrogen gas.
Okay.
So when I say gas, please keep it in mind that I'm talking about atomic hydrogen or H1.
Okay.
Yeah. So we'll take the average gas content and average star formation rate and correlate them, and just see what we get. Maybe this is just a complementary approach which we want to try out, because we are suddenly getting hold of this database where we have this huge number of statistical things. We can do it again and to see how it goes. So we decided to start with this alpha survey, which was available. It's a very sensitive survey. The problem is it's sensitive for a reason, because it was done with this huge single dish, which means the beam, or the equivalent to the point spread function of optical surveys, is quite large. It's actually larger than 3 arc minutes. So it's quite big. So what happens is, and it only covers, as I told you, because H1 is a faint line, it only covers up to Z of 0.06. So we are doing the first thing of the very nearby galaxies and doing this comparison to build up for hopefully future work. So because the beam is so large, if you look at a group, what it happens is it's very difficult to look at just one galaxy in that group. What is happening is it's adding over all the galaxies inside that group. So this is actually the correct kind of data set to try out the method I just said, because you're taking the entire information from the group area. So that's how we wanted to use alpha. So this work is mainly using alpha, the little bit of Dingo data that we have used, only 18 hours of data on the first pilot data. And what we did was, if you please go to the table 1 and the next page, so you can see the area of the sky we're looking at are 3, in table 1, you can see 3 G fields named. These are actually from the Gamma survey, Galaxy and Mass Assembly survey. They have wonderful ancillary data from stellar masses, star formation rate, group catalogs, etc. So there's a slight overlap between 3 of the Gamma equatorial fields, which are relatively small fields, about 10 degrees square degree, so 40 square degrees each, something like that. A little bit more than that, relatively small field, but they have a slight overlap with the alpha survey. So we looked at that area where there is overlap. So we have information about the galaxies and their environment, etc., from the Gamma survey, and get the H1 from the alpha survey. For isolated galaxies, not a problem, but for pairs and groups, you can see the figure 1 just to the right. This is basically in the x-axis, the redshift, of course. In the y-axis, I've approximately plotted the diameters of the isolated galaxies in blue, the pairs in open green circles, and groups in filled red circles. So what happens, those black lines, two black lines, are more or less the size of the beam, the two axes of the beam are receivable. So isolated galaxies more or less are, of course, absorbed in them. But for pairs and groups, many of them are actually almost totally covered by the beam, which are the ones which are not totally covered. You, of course, add in quadrature the radii of the beam and the radii of the group and cover the entire area, typically with a few beams. That's all. And you take that entire area and basically you get the entire H1. Now we can zoom out. And so this is the idea. So let's start with the alpha first.
Okay.
We'll look at these groups and pairs and isolated galaxies. We'll take their total H1s and divide by their total stellar masses as tabulated from gamma. We know which galaxies form those groups. We take their total stellar masses. So when we take the H1 spectra, you can slowly go down extracting the H1 spectra bar. So when you're taking the H1 spectra, we reduce the dimensions right away. Means we take actually spectra, not keep it as two-dimensional cubelets. We just decided to, anyway, we had to reduce the dimension at some point. So we just took the H1 spectra of the galaxies, isolated galaxies, pairs or groups, normalize or directly divide them by the stellar mass of that particular galaxy or the group or that pair. These are our basic information. Now, still that is not enough because we are looking at pretty faint lines spread across a lot of galaxies, etc. So we have to use stacking. So we will stack the lines, but in what regions or what galaxies do we club together to stack the lines? So to do that, again, we took a slightly new approach. So we are working with average quantities. So if you can please go down and go to figure 2.
Yeah, average M, the star formation plane, figure 2. There we go.
So in the next page, yeah. So you can see, so the top left is isolated galaxies. The other two are pairs and groups. For isolated galaxies, it's the standard log star formation rate versus log stellar mass plane. This is a very well-known plane where that red line running across kind of marks the star forming main sequence. Right. So that's well known that most galaxies kind of evolve around that sequence and probably then drop off that sequence as they get quenched. This is more or less the idea, right? And since these are star forming galaxies, we're not really looking at red and dead galaxies. We're looking at the galaxies which are star formation, right? So now in the pairs and the groups, instead of the totals, we have now plotted average star formation rates. As you can see from the axes, they're exactly the same axis. Only the star formation and stellar mass has converted to average star formation and average stellar mass for groups and pairs. And probably not very surprisingly, they also occupy these average values, have a very similar distribution. They also seem to cluster kind of around the star formation main sequence because this is basically an averaging of things that you're seeing for all galaxies, not necessarily the isolated galaxies, which have a similar distribution, right? So, but still, it was not very clear before we actually did it. So it seemed that they seem to very nicely cluster around.
Yeah.
There is sorry, you were saying?
I'm good.
No, okay, yeah. So there is also, these have been color coded according to the G-R color. We have not pushed in any way towards it, but because it's not a very good indicator, but there is something very obvious to your eye as you see it. They go from blue to red as you go from the left of the figures along the star formation main sequence, which is that red line. That is the star formation main sequence from Davies et al. 2016 for Z below 0.1, all galaxies below 0.1, that red line. So they seem to be on that line, and then there is a red kind of turn off. So we put it in this discussion section too, that this is something for future. This might be another indicator of even groups and pairs overall might have a evolutionary, they can be maybe followed in an evolutionary way on thus this sort of a diagram, like we tend to think of galaxies, but we don't want to push it because it's just a conjecture at this point. But what we do though, we break up this plane into various regions And basically, those R1, R2, R3, 4, R4s, just to, that it will become clear later that R1 and R3, you can see there is like a line in between. So we basically define two R1 regions and two R3 regions, as Frank is showing on the left. The reason is that there are more isolated galaxies at slightly lower stellar masses than pairs or groups at those stellar masses, around 10 to the power 8, 8 on that log scale. So what happens is the median value of the bigger R1 and R3 box is kind of a little lower than it is for pairs and groups. Just to make sure we're comparing apples with apples, we also define a slightly smaller R1 and R3 for the isolated galaxies to make sure that the median values are very similar for all the things. This will come to it. So what we do is we basically, I told you the spectra from alpha alpha, where we have taken, whether it's an isolated galaxy or a group or pair, we have taken an entire spectrum over the group area. Most of them look noise-like. They're often on a slight detection. You have normalized them or divided in each case by the total stellar mass of either it's a group, pair, or it's a galaxy, it's just the stellar mass. Now you take all the groups, all the pairs, or all the isolated galaxies in any particular region, and you just stack them with the corresponding weight given their original quality of the spectrum as measured by the RMS in the spectrum, basically. So you don't do based on the luminosity, because it will basically bias you again with redshift. So you just basically give a weight based on the quality of the spectrum, how noisy the spectrum was. That's basically it. And instead of going through the long table, we'll maybe go to figure 3, which is the result from this first part, which will already kind of, I'll maybe come back to table 2, but before that, yes. Cool. So the top 2 are isolated galaxies, top 2 panels. Left is that bigger region, right is the smaller region. And by eye, you can see that the stellar masses, for example, in the median stellar masses in each region in R1 and R3 are very comparable to the median stellar masses for pairs and groups, around 10 to the power 8.8 or something, right? You can by eye. But for the bigger group, it's slightly to the left. That was the reason it was done. But now they have been color coded by simply the mean H1 fraction that we have measured. So what we are seeing is to the right, towards the right, R2, R4, R5. The mean H1 fraction steadily decreases as you go from higher star forming galaxies or pairs or groups down. Not only that, the values are very similar to each other across the units. That means isolated galaxies in R2, pairs in R2, and groups in R2 have very similar values. The interesting part comes though in the R1 and R3. No matter whether you're looking at the larger region where you are actually sampling for isolated galaxies, lowest stellar mass galaxies which tend to have most gas, as has been shown by many studies, or even the smaller region R1 and R3, which you're restricting yourself to not that maybe gas-rich galaxies, we are finding a much higher gas fraction completely counterintuitively in groups especially. Pairs are somewhere in between. So you can see it's quite red and orange for groups. So this was the first surprise. What exactly is going on here? I'll quantify this difference a little later. So just to study this particular trend, and as you can see in R5, it's almost consistent with 0 for all the galaxies. Basically, we're looking at either galaxies, isolated galaxies, or pairs or groups, no matter for which we are looking at R5, consistent with the member galaxies not having much gas. So they are basically the galaxies probably which are dropping off. As we said, these all have measured star formation. So these are not really the dead galaxies, but going there, maybe the Green Valley galaxies.
There you go.
Or pairs and groups with those kind of things, right? So that part is not any more interesting. The interesting part is around that red line, the star forming main sequence as defined from galaxies, which these average values also tend to follow for pairs, right? So now, if you please go to figure 4, what we did was we now divided the sample in a slightly different way to explore this particular fact, that why are we finding such high, this figure, high gas fraction at the low stellar mass end. So we basically now divided up it into regions along that star forming main sequence. And to repeat the exercise. Uh, Let me just point out that these regions look a little arbitrary. They were arrived at both for the previous results I show and what I am going to show now for this figure, with a little bit of experimentation, so that we have enough signal to noise ratio. Basically, we have enough groups, especially groups. This is a small region of the sky, and especially groups, so that we have a very nice detectable signal. So this was the main. So this one is for this particular figure on the main sequence. As you can see, the groups are the regions are much more equally or equally spaced. That was also intentional, because we wanted to actually measure how it changes in a continuous way. For example, you can quantify now this along with stellar mass, because we are always measuring on the star forming main sequence. Now we can quantify how with stellar mass this gas fraction might change.
Okay.
So the results are in figure 5, which I consider to be the one of the more important figures in this paper. Yeah, figure 5 there. And now we have completely concentrated on the star forming galaxies, so to say, on the star forming main sequence. So you can see the red and green are groups and pairs. Remember, we are measuring everything that is within a group. Yes. And dividing by the stellar mass of the catalog galaxies. I'll come back to this point later. Total stellar mass of the catalog galaxies, of course. Galaxies we know to be part of those pairs and groups. And then compared to the isolated galaxies, also plotted are points from some previous studies, which have actually either used alpha data or used data from, for example, that's from the French telescope. I'm forgetting the name. I'll come back to it maybe sometimes later. Anyway, so these are previous studies which have tried to look at the same trends. So our isolated galaxies quite well match the gray and the kind of beige points. Okay. The blue, right, even to the very low stellar masses. But for those low, now remember, for pairs and isolated galaxies, the quantity is average stellar mass. We have to compare similar things, especially for the lowest bin, around 10 to the power 8.5. You can see the red and green points are quite high compared to the blue points. Yes. So the gas fraction counterintuitively. Why counterintuitively? Because previous studies have found that in group environments, in dense environments, the gas in galaxies tend to be a little less, actually.
Okay.
If the disks are a little smaller, which makes sense based on the introduction we talked about, because of gas being stripped away on various kind of processes. So what's going on here? So couple of points just to follow up on this plot. Pairs are behaving a little erratically. So the green point is very close to the red point in the lowest bin. Then it comes close to the blue point. So one possible reason is in just the adjacent figure, in figure 6, which is just adjacent to figure 5. Yeah. So here for various bins, for groups, I have plotted how many cataloged members galaxies does the group have. Okay. So for the lowest bins, you can see blue dominates, which is only 3 galaxies. Yeah. And pairs are effectively close to that regime, right? So probably in the lowest bins, you can understand whatever is happening in groups probably are happening also in these pairs. I'll come to the next plot soon to more further follow up in this point. But as we go to, this is an interesting point to plot, because you can kind of see that as you go in higher average stellar mass, the groups become bigger actually. So, and larger number of members. And if you remember, they also, the median colors that I had plotted becomes also redder. So probably this also is an indication of an evolutionary thing. Maybe these small groups, maybe more gas-rich groups towards the right, larger groups, maybe definitely gas-poorer groups, but of course they have very similar properties to pairs and isolated galaxies. If you can quickly move to the next figure also, next page, right next page, figure 7.
Sure, figure 7.
Yes, so that in this figure, what I've done in those same 5 regions along the star-forming main sequence, I plot the ratio of the 2 pairs, stellar masses of the 2 pairs. So, yeah. So if the mass ratio is generally greater than 1:3, you can consider that them to be major merger candidates. Anything lower, you consider them to be minor merger candidates, especially if they're in the blue regime, less than 1:10. So for the lowest bin, most of them are like that. Actually, the disparity in masses is quite large between the two pairs in the 8.5 average stellar mass regime. And minor mergers are known to be gas rich many times. Because so that is another indicator of why pairs are also very deviant in that very low average stellar mass regime. And as they become higher, they become more less interesting and maybe more major merger candidate pairs. So this is the thing. But now, as I told you, the whole study took this archival data set to try out a complementary approach. But the restriction of the data set, or the limitation of the data set, is that huge beam. We cannot separate the galaxies out. Now here, the first DINGO data we had in hand, it was only 18 hours. On one of those gamma fields, if you can zoom out to the right, just to this, or just to the figure to the right, figure 8. Here, that black line is the DINGO resolution now, which is 30 arc seconds. And now, what are plotted are the diameters of the galaxies in groups, pairs, or if they're isolated. And in most cases, you can see many cases, they're not resolved. So now we are in a much better resolution. Some of them are a little bit resolved. We have to live with it. But the resolution is such that you're unlikely to have galaxies overlapping each other in resolution. So that's the great thing about now. So DINGO will do these things, like do these deep surveys, but at such good resolution. So we can now choose on galaxies. Now that this is the initial DINGO data, so we cannot repeat exactly what we did for alpha, because if you do the comparisons, it's still only 18 hours is almost 50 times less in sensitivity than alpha, but 6 times better in resolution. That's why the sensitivity needs to be much higher. We'll get there. But what we can definitely do is do the same stacking procedure, but now pick up only the spectra from the galaxies. So now we'll look at groups and pairs like before, but we'll take the spectra from the galaxies from those groups and pairs, add them together. First step, add them together, because we're interested in the total gas from the group and the total pair gas from pairs, same as in alpha. Divide again by the total stellar mass of the catalog members, same as before. And now, if you can please move to figure 9. So just next page, figure 9. And now we'll do the similar study, but over the say star forming main sequence. These are now from the DINGO in the G15, and one of the same regions that was studied with alpha, which had a partial overlap with alpha. This is now the full region because we had targeted it and covered it. Also, the redshift is slightly larger. We have gone from 0.06 to 0.09. I'm using all of it because not much is changing in this small redshift range in terms of overall properties. That is known. H1 is actually quite flat, H1 content for a long time. But more importantly, just to have enough number of, as you can see, groups, just to be able to do the stacking and to do a first comparison. So we have now, instead of looking at the total content of gas and in pairs and groups, we are now taking up the gases from individual members, each one spectra, co-adding, dividing by the total stellar mass, and again stacking on gas fraction, get the average gas fraction.
Yes.
So we actually, just to make again like to like, these regions you can see are slightly different from the previous regions I was showing, there were 5 regions on the main sequence, previous figure. We overlay the same regions on the alpha data too, and exactly repeat what we did for alpha, but for these regions.
Yes.
So now we have like to like, and we compare in figure 10, which is probably the most important figure of this.
Here we go, money shot.
Yes, of this paper. So this is figure 10. And now you have alpha, the previous data set in open symbols and DINGO in closed symbols. Suddenly, that difference is gone. So when you're looking at galaxies themselves, For
Right.
groups, which is that maroon point, it's not up there with the red point. It has come down.
Yes.
Right? And not only come down, it is probably a little lower than the blue point, dark blue filled point, rhombus.
Yes.
Yes.
Bingo.
Though statistically, this particular study doesn't have the significance, but this has been shown, as I told you previously by previous studies, that actually if you look at galaxies in groups, their gas content, especially satellite galaxies in group and compared to isolated ones, their gas content, let's not put satellite, let's put satellites away. Galaxies in group and outside, and plot them in stellar mass and look at the gas fractions, their gas content is slightly lower. It has been shown. So we're seeing the same thing.
Yeah.
Everything is consistent.
Cool.
So there is a difference. So this is the main thing. There's a difference between what we get from alpha and dingo. There's a difference in what we get when we stack over the entire group area with a sensitive survey, which still exists, and just the galaxies in groups and pairs. Here, if you will notice also that the alpha-alpha pair point is slightly in between, because this bin, this region that we're looking at now, in dingo and alpha-alpha, is somewhere in between the lowest two bins in the previous plot that I was showing you, which was, if anyone is interested, if they can look at figure 5. So it is kind of an average of, you can please quickly go back to figure 5.
Yeah, okay.
Yeah, so it's kind of the average of those two lower bins. Because we have moved a little bit to the right now. You can see it's the span, those lower bins span from about 8.1 to 9.1 on the log scale, right? And if you go back to figure 10 now, yes.
Yep.
They span from around 8.5 to 9 point something. So a little bit to the right. That's why already pairs are falling back towards the trend for normal isolated galaxies. So that's why it's somewhere in between. Pairs always hang out. So the main, but it's very clear. You can see from groups that there is a difference. In all of these data are given in the paper in long tables. All of these values are marked with the associated errors. We have reduced the errors through bootstrap resampling, etc. So if anything, we have overestimated the errors rather than the other way. And so these are quite robust, whatever we are seeing. And we have also, in each case, there are these stacks are also available in the appendix of the paper and as a figure set. So you can go and look at the stacked spectra. And you can see that each stack spectra is fitted with a Gaussian, and all the channels that fall within plus minus 2 sigma of the center of the Gaussian are added together. This is how it's measured. And sometimes due to the velocity widths have themselves a trend, which is discussed in the paper, which I don't want to discuss much here because the velocity widths can be a little tricky, because when the detections are not always very are sometimes marginal, these velocity widths can be misleading. But generally what happens is for the alpha-alpha studies, the velocity widths increase as you go from isolated to pairs to groups, which makes sense, kind of. You have more things added up. But when you're doing the dingo study, since you are stacking on galaxies literally, you are basically coordinating the data of galaxies. You have brought all of those galaxies, ignoring the group velocity dispersion, on the same velocity. If you're writing up, actually the velocity widths decrease as you go from isolated to pairs to groups, which is again one of the indications that probably groups, the same thing that you see here, galaxies in groups have a little less gas than in isolated.
Yes.
And it's not as spread out, which is another indication, but we don't I don't discuss the velocity things too much because and here also I won't go to figure 11. This is very similar to what I was showing, how many group multiplicity, how many. You can just move to the slide right, please. You can see it's a group multiplicity in these 3 bins. The lowest one is dominated by very small multiplicity groups, the right, and it goes to higher multiplicity groups as you go right. In table 5, we kind of quantitatively give the differences, and for groups, even considering errors, it's can be twice, basically 100% difference. If you take 100 minus 114, it can be at least 100% difference. So the point is, in the discussion, we try to understand what's going on here. As I said, the first point in the discussion that we discuss is this issue that for about average stellar mass of 10 to the power 9.5 in solar masses, those kind of groups seems to have a lot more average H1 per unit stellar mass than in isolated galaxies.
Okay.
It's not that this is something completely new, because the clues were all around. There were many previous studies which were stumbling across it and have found it. There have been studies of Higgs and compact groups, exactly similar studies comparing single dish and interferometric data, which seem to show single dish data have much more gas. There have been looking at in directions where there is strong absorption against a background quasar by gas, DLAs, magnesium absorbers, etc., even Lyman limit systems, Lyman alpha absorption, etc. There have been, when things have tried to be followed up or statistically looked at, etc., many times it seems that the absorption is coming from the intergroup medium of especially low multiplicity groups. Similarly, for molecular gas absorption, at least till redshifts from z equal to 0.9 to, okay, so if you want to show the discussion, I'll quickly give you exactly where to go. It's on page 14, right on top.
Yep.
Page 13, right at the end, to page 14, right on top. The things that we discuss is so page 13, if you go right at the bottom of page 13, there's a previous page.
Oops, sorry.
Yeah, no problem. It is a long paper, but we had to discuss a lot of stuff to make it for completion's sake.
Yep, absolutely.
Yeah, so MG2, as you can see, from 0.19 to 1.5, there have been indications that there is this coming from diffuse gas in between galaxies, that in groups or even in pairs. And just on the next page, top left, as you can see, even for CO emission, it seems there is molecular gas in between. So there has been indication. Now, of course, the other things like the gas fraction decreasing with increasing stellar mass, etc. These are either expected or similar things have been found previously. What is interesting is that at the higher average stellar mass, which is just stellar mass for isolated galaxies, the values are so similar for the different kind of galaxies. Does this indicate that doesn't matter whether you are in a group or a pair, you'll end up in the same place? Maybe it does. Maybe that is an indication of the same thing where we started. That whatever happens, probably there's a lot of gas anyway floating around. Probably that gets, and that gas floating around, maybe this this gas in between. But there is another possibility, of course, which is just in the previous page, in the page 13, where we discuss that what if, due to the limit of the gamma survey itself, we have not cataloged some very faint galaxies, which have a very high gas fraction. They have to have a very high gas fraction. So we try to do a simple calculation by extrapolating the known trends of stellar mass versus gas fraction. So you will need, but the gamma's stellar mass completely luminous is quite high. It actually in the optical band, it can go up to 2 magnitudes deeper than SDSS. So it's a very deep survey. So it goes, so our stellar mass limits goes from 10 to the power 7 to 10 to the power 8 at 0.06 for the alpha data, where, and so you need, so say suppose these galaxies are just below that limit, say 10 to the power 6.5. You still need a bunch of them, about 10 of them. So the exact number is, I think, given here. I need around 11 of such galaxies which have to be all gas rich with quite a high gas fraction, above 100. 120 actually, which can happen by extrapolating present trends, but we don't know really. We have to check that. So
Right.
we need very high gas fraction galaxies sitting there. Or maybe a more likely explanation is that they are indeed of tidal origin. And we also discussed that if you want to take this discussion in terms of an evolutionary trend, maybe if you kind of at least indulge me and think of it in that way, that maybe small groups assemble first from gas-rich galaxies. Their gas floats around within them or pairs. Then, because they have been disturbed, they lie in intergalactic space for some time and probably get ionized, probably get dispersed, especially once a BCG has an AGN maybe. Once the bright and or falls into a group which has a AGN or has a hot intergroup medium or etc. etc. And that gas gets basically dispersed, and maybe then all evolution happens in a way that at the end it doesn't matter on an average whether the galaxy lies in a group or a pair or isolated. They have end up with very similar relation between star formation and stellar mass and gas, the H1 content that they have. So this is a hand-wavy way that we have that seems to make sense, but of course much deeper things need to be done. In this discussion section, we also kind of mention the other things that I've already mentioned to you, that that we do see the trend of isolated galaxies being a little gas-rich than galaxies in groups. Yeah, this is on page 13. All this discussion is on page 13, if just previously. If you go back to page 13 and then etc. And the fourth, that as you move away from the star formation main sequence, you do seem to that the kind of all doesn't matter whether the galaxies are isolated in groups or pairs, they get depleted of gas. And so that's a very similar trend. These are the higher stellar mass bins, which we're saying were very comparable, very similar to this. We do I'm hoping, I think I've taken a little longer, but I'll try to wrap up quickly.
Oh, good.
We tried a couple of things to see if there are internal trends that are basically we are missing and which are affecting these things. Like in section 4.1, we divide all groups into either, this is page figure 12, yes, that figure, either groups which have so the upper two panels, either groups which have only 3 members or 4 or greater members, to see if that's only 3 members or groups with low multiplicity drive the trend. And if you go to the figure 13, for example, we see no, it doesn't matter. If, even only 3-member groups at higher stellar masses also have a pretty low this thing, which are exactly comparable to the isolated galaxies or pairs or groups, etc., or pairs, or that for n equal to 4 groups. We also, one hidden thing I've not talked about, which we very consciously avoided, was halo mass. The reason being, we had a lot of pairs, we had a lot of n equal to 3 groups, etc., for which you cannot calculate halo mass from dynamics. You need at least 5 or more members. Otherwise, you have to do a statistical exercise, which was like abundance matching, which inherently has its own uncertainties. So we wanted to keep it an empirical study. So that's why we took average versus average. But in figure 14, what we've done is simply for all the 5 regions on the main sequence, which we discussed some time ago,
yes,
those different regions, you can see that the what we have plotted is the stellar mass of the blue compact dwarf galaxy against the total stellar mass. Now, if you go just to see how much difference in halo mass might there be between say groups in different regions or isolated galaxy in different region, etc. So that this BCG stellar mass is the determinant of the halo mass, which gets a correction on top of that. Say, for example, from the difference in luminosities between the BCG and the next brightest member. That is represented by the color coding, which is the difference in color. So all the isolated galaxies will lie on that black line because their stellar masses and total masses will be exactly the same,
Yes.
right?
Yes.
And the regions are marked by those dashed lines in each panel. So each panel is a region, covers one region.
Oh, yeah.
And the pluses are pairs and the dots are groups. Of course, the total masses of pairs is greater than their average mass.
Sure.
The total masses of groups are even greater than their average mass, right? But in all cases, it doesn't happen that the BCG mass is it's always within that region, a region defined by the average mass, basically. The BCG mass always lies within the region. So that actually the halo masses in some sense should be very comparable. If not across regions, across types, means isolated galaxies, pairs, or groups, at least for one type, say within groups, within a region, we are looking at a certain kind of halo mass. So this, for within a certain kind of galaxy, a certain kind of data set, like for groups, this definition that we have done, average stellar mass, is actually looking at similar types of having similar halo masses also.
Okay.
But this becomes more interesting. We did some comparison. If you please move to figure 15 now. We did some comparison with an in-house semi-analytical code that we had in Perth, which is the SHARC model. There are issues both with semi-analytical and hydrodynamical model to consider gas in between galaxies, intergroup medium, intercluster medium. There are a lot of, what should I say, knobs which can be adjusted, which can create issues. So we just looked at galaxies, the gas content within galaxies, and tried to see how these trends will vary on these average planes for isolated pairs and groups as you keep, for example, the stellar mass fixed and vary the star formation rate, or keep the moved along the right panels, moved along the main sequence, the same thing that we're doing. And we see exactly this is the kind of thing that happens, that as you move, you'll see that the stellar, the gas fraction will increase. You'll see that if you go to higher stellar masses in the left panels, higher stellar masses, the gas fraction will be lower in green than at lower stellar masses, the gas fraction is higher in blue. These kind of trends, you exactly see these things that we saw. Mm-hmm. Of course, when you consider the gas in galaxies, you see these trends. Of course, these presently cannot help us with our main issue, which was what is the gas in between, where is it coming from? Yeah, but it's good to see that the trends are good. But the next figure is also, I think, very interesting, figure 16, where from this figure, from SARC simulations, what we do is we plot the average stellar mass that we have for the 3 different categories from the galaxies and SARC and their halo masses. Now look at the green line for all the points. Okay. The green line basically are for units, groups, pairs, galaxies lying just above the main sequence, highly star forming. For all of them, the halo mass actually is quite flat, especially beyond 8 in log scale. Right? Beyond 8 in log scale, it's quite flat. Yeah. The halo mass is very similar to the average stellar mass. Not average, similar to the average stellar mass. The halo mass is very similar for the same average stellar mass across units, isolated pair and groups. Yeah. This is just a thing, again, we have considered this and put it out there, that our trends are dominated by this kind of system because these are just above the main sequence on our region. These are the most gas-rich systems. And it might turn out that it is difficult to clearly measure it for the kind of, because of the low multiplicity and most pair dominated and isolated galaxies, of course, system that we have. But it might turn out that for this kind of, this just above the main sequence, they have very similar halo masses also. So halo mass might have something to do with our trends, and it is actually might be built into our trends. Now, of course, you can understand the only way to differentiate these is to break it up into thinner slices along that plane. Do it again. And this is exactly what we hope we'll be able to do as more and more data from DINGO gets collected, and we can actually get detections over entire group or pair areas, because it's mostly noise, right? When you look at galaxies, we're getting the gas, but in the group and pair areas, even if it's there, you really need to reach that sensitivity level that alpha reached with a much coarser resolution. But now we'll be able to, with the same data set, divide it up. This is the hope. So we are kind of concluding now and moving on to the next. Maybe you can also move on to the next page, and where the summary is given. And also we can discuss this after the paper ends, how to look for this extra gas and what we are thinking of doing. But definitely this paper is a marker for what we will do with Dingo, me or someone else in the future. We have to wait. We have to wait for the Dingo to. We already have on a different field 50 hours of data, but this is only pilot survey. Hopefully, the main survey will come in a year's time, and we'll start observing. SK will. So there is a lot of unexplored space out there vis-a-vis atomic hydrogen, and hopefully we'll find something interesting. And that's, I think, interesting about being an empiricist. I consider myself an empiricist. Go and look there and you'll always find something interesting. So hopefully you'll also, or your viewers will also find it interesting, and they can take a look at the paper, and I'll be very happy to get feedback on it and what people think.
Very cool. Very cool. Sambit, thank you so much for walking us through your very lovely article.
Sure.
And you touched on it a little bit there at the end. So maybe just expand on that just a little bit. So where do we go over the next 2 to 5 years? You mentioned, additional surveys coming up. Are there other things, or like there are additional simulations that could be done to help detangle some of this?
So I'm not the right person to answer the question on simulation. So I'll first stick to the observational part. As I mentioned, 2 to 5 years is kind of the timeline we're looking at to have a lot of Dingo data in hand. So it's our survey itself. So Dingo will be a major advantage and this Dingo survey focuses on these gamma areas. It's basically built on the gamma. So we have all this ancillary data in hand. Everything is ready. You just bring them and add them together. You're doing it. Okay. So this is for this particular study, and it, finer similar studies, dividing up the parameter space into finer regions, etc. We're dividing up the sample into different properties and studying, even probably, hopefully, with redshift, because we are just looking at the very local universe now. Dingo is starting to do, especially with stacking, we'll be able to do it, as I said, about 0.5, a little less maybe. But so we'll move to redshift, and if we see an evolution with redshift, that's one of the things we're going to do. We are also doing targeted observations for some of these low mass groups, trying to, with existing instruments, and another very powerful, we hope to do it with another very powerful interferometer, which is a SK precursor, which is in South Africa, which is called NIRCad. We try to do it. So to basically try to look for this gas in between these galaxies, between the galaxies in these low mass groups. Maybe even follow up with deeper optical observations to see if there are like galaxies we missed.
Okay. Yes.
Optical or other bands. So that's the other side where we'll focus on these low mass groups. So this is the second thing. And personally, I'm also taking another step with Dingo. I'm adding molecular hydrogen data to this.
Okay.
Because as I told you, molecular hydrogen is the phase which is more directly correlated with star formation. So we already have completed a kind of a pilot survey with the Atacama Pathfinder experiment, which is a single dish doing millimeter studies in Atacama Desert, like beside ALMA, and we already have started a survey on ALMA, which is Atacama Large Millimeter Array. So we're trying to add molecular gas data to kind of add that element to, and see, especially if there are many questions here, as I told you, about how gas is fed into galaxies, how gas is converted from unusable gas to usable gas, which will form stars, if you want to say that, especially in centers of galaxies. These needs measurements of a uniform kind, and the thing that was missing till now was H1.
Okay.
In large number of galaxies. And now that you have the base data set like Dingo, and maybe more surveys in the future with SKA, square kilometer array. We'll be simply able to add, because the other things, molecular gas and stellar information is slightly easier to get, or already exists in many cases like gamma, and you build on that. So now we can add all that together and try to open some of the knots and try to just
yes, some of those knobs and figure out what's going on there. Yeah. Very cool. Very cool. Well, I really look forward to seeing this work develop, or this body of work develop over the next couple of years as this new data set comes in and we got new telescopes going on. So it'll be very exciting to see how this develops over the next couple of years. So very cool. Sambit, thank you so much for walking us through your very lovely paper.
It was, as I said, it was a pleasure, and thank you again for having me here. I hope people find it interesting and get in touch with their ideas, and
feel free to reach out. And that'll do, everyone. Thank you so much. Bye-bye. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.